So today we are going to discuss about the distributed deadlock detection, distributed approach for the deadlock detection. In the centralized approach, we have seen that there was a central coordinator and every site is maintaining their WFG and sending the message individually to the central coordinator, and the central coordinator will be looking for the union of the different WFG which is obtained from the different sites. If there is a cycle or there is a deadlock is being detected at the local stage, it is served locally. Otherwise, the central coordinator has the responsibility to take care of all the WFG and then try to find out whether there is a cycle created or not, and then it has to resolve that problem. Besides that, in distributed strategy or distributed approach, each site of the system has the equal responsibility as far as the deadlock detection is concerned, and all sites are going to cooperate in detecting the cycle in their state graph. Of course, there will be many sites, so every site has the responsibility of detecting the deadlock. So it can be initiated whenever a process is forced to wait. If process has requested for a particular resource and it is not available and it is wait state, in the wait state from a long time, it can initiate. It can also be initiated either by the local sites of the process or by the sites where the process waits. The site can initiate the process, or at the particular site where the process is waiting, that process can initiate. We have 4 different algorithms related to the distributed deadlock detection, and the first one is the path pushing algorithm. Second one is edge chasing algorithm, diffusion computation, and the global state detection algorithm. So we are going to discuss the first one, that is the path pushing algorithm, that is WFG based distributed algorithm for the deadlock detection. Now, as we have seen that in the centralized approach, we have a WFG based distribution algorithm where each site is going to maintain its own local WFG. However, in this particular case, in the distributed algorithm or in the distributed approach, the model in which the model of the waiting situation that is going to involve the external processes besides the local processes is little bit modified in the modified form of the local WFG at each site. And this modified WFG contains an extra node, and that node is known as PX. PX stands for the process which is not available in that particular node. It is by that particular site, but it is available at another site. So an extra node, that is PEX, is added to the local wait for the graph of each site, and this node is connected to the wait for the graph of the corresponding site in the following manner. There are 2 versions of that. The first one says that if an edge from PI to PEX, where PEX is a newly introduced node. So an edge PI PEX is added if the process PI is waiting for a resource in another site being held by any process. The meaning thereby, if PI is a process of a site, suppose S1, and it is waiting for a resource, and that resource belongs to another site, and that at that site that particular resource is held or held by another process. So in that case, we will put an edge PI to PEX. The second point says that we have to add an edge PEX to PJ. This edge has to be added if PJ is a process of another site and which is waiting for a resource which is currently held by the process of this site. meaning thereby this PEX PJ edge will be added if and only if this process PJ, which is of another site, and it is waiting for the resource which is currently held by this site. So with these two manner, we are going to include a new, that is new node, that is PEX node. And how it is being done, let us go with the example, then it will be more clear. Suppose we have two sites, S1 and S2. This is S1 site and this is S2 site. And this S1 and S2 site is maintaining its local weight for the graph. This weight for the graph says that P2 is waiting for P1, P3 is waiting for P2, and P2 is waiting for P4. This is the local WFG which is maintained by the site S1. At site S2, P1 is waiting for P3 and P3 is waiting for P5. So this is the modified WFG by using the principle which has been explained right now, by introducing a node at the two different sites, that is PEX node, and how to include that node and how to connect the edge will depend upon these two criteria. Now, let us discuss the first, that is what is happening at site S1. Now, in this WFG, which is the WFG of the site S1, an edge is being added from P1 to PEX because P1 is waiting for a resource. P1 is waiting for a resource in the site S2 that is held by P3. So that is why we have put P1 to PEX as an edge. And there is another edge from PEX to P3. It is added because P3 is a process of the site S2 at the site S2, and that is waiting to acquire the resources currently held by the site S1. Now, P1 is waiting state because P3 is holding something. So that is why we have included this edge. And P3 is also waiting for P2 in this particular site. So we have to include this also. So P1 to PX and PEX to P3 has been included. Rest of the edges are shown as it is, whatever the local WFG explains, that is P2 to P4, P2 to P1, and P3 to P2. It is written as it is. Now let's come to the site number 2, that is S2. Now we have an edge from P3 to PX, because this edge is added because the process P3 is waiting for a resource. Process P3 is waiting for a resource in site S1. Process P3 is waiting for a resource at site S1. So P3 and PX will be an edge in this. And this source, which is P3 is waiting, it is held by the P2. And there will be an edge from PEX to P1. This is being added. Why? Because process P1 in the site, process P1 of the site S1, that is waiting to acquire a resource currently held by P3. P1 is waiting for P3. So that is why P3 to PX and PX to P1, it is being added. So this is the local WFG, but this is modified WFG, which is maintained by the individual site by including a new node, that is PEX, depending upon these two criteria, these two principles, you can say. Now, if the local WFG contains a cycle, now the algorithm begins, and the algorithm begins in explaining these points, that if a local WFG contains a cycle that does not involve PEX, but in this case it is involving, because this is framing a cycle. but this is framing a cycle because and PX is involved. So this is not for that. So if there may be a situation that local WFG contains a cycle that does not involve the PEX, a deadlock that involves only the local processes of that site has occurred. Such deadlock can be locally resolved without the need to consult to any other site. Meaning thereby after making the modified WFG, if we are getting any kind of cycle without involving PEX, then it will be solved, the deadlock will be detected and it will be resolved by the site S1 itself. That is what is the meaning of the first part of the algorithm. But if a local WFG contains a cycle that involves the PEX, as you can see here, then there is a possibility of distributed deadlock. It may be possible that there may be a deadlock. So to confirm it, the detection algorithm is invoked by the site whose WFG contains the cycle involving PEX. So there are two points. One is if the cycle is involving any, if the cycle is in, if there is a cycle in the WFG which is not including PEX, it means it is the local deadlock which has been created because of the local processes. But if it is not so, no problem. It has to be resolved by the site itself. But if there is a local, there is a cycle existing at the local site involving this PEX, then there is a possibility of the distributed deadlock. And for that, we have to, for whether this deadlock is actually happening or not, or it is available or not, or it is happening or not, to confirm it, detection algorithm or detection of the deadlock algorithm is invoked by the site whose WFG contains the cycle involving the PEX. Now, this site has the responsibility to invoke the detection algorithm and to confirm it. So now the algorithm begins. This is the explanation, and the algorithm begins from this place. It says that how it will go, how it will proceed once the S1 is getting that by including PEX, it is getting a cycle. How it will proceed to confirm with the detection algorithm. So suppose we have a cycle PEX, PI, PJ, and so on, PK, PEX. It is detected, which means that this PK is waiting for the resource belonging to the other site SJ. This is site SI and this is site SJ. So it means PK is waiting for the resource belonging to other site SJ. So the site SI sends a deadlock detection message to the site SJ, which contains only that part. Means whenever it will send the message, it will send the message, and in that message, it will send the WFG, and that WFG, with only that part of the WFG that forms the cycle, meaning thereby this is the WFG of site S1. So only that part which is framing a cycle that is sent to the site S2. So I have given an example, and with this example, I'm trying to explain this one. That suppose site S1, what a site S1 will send the message because it has detected a cycle, and that cycle is PEX, P3, P2, P1, and PEX. So it will send a message PEX, P3, P2, P1, and PX to the site S2, since P1 is waiting for the resource at the site S2. So that is why it will be sending the message in the form of these 5 entities. The cycle which is being framed along with PEX, P3, P2, P1, and the PX. Now, whenever site SJ is going to receive it, when the message is received, site SJ updates its local weight for the graph by adding those edges of the cycle that do not involve the node PEX. Whenever it will send this information in the form of a message to the other site, and whenever that site receives that message, it will include those edges which does not include with this, which does not involve the node PEX. So the node which is not involved is P3 to P2 and P2 to P1. These are the 2 edges which does not involve PEX. So these 2 edges are included at site S2. So P3 to P2 and PT to P1 is being added. So this is the WFG of the site S2 after receiving the deadlock detection message from the site S1. Now the newly constructed wait for the graph of the site Sj, suppose in this particular case it is site S2. So newly constructed WFG of the site Sj, if it contains a cycle that does not involve the node PEX, then it means a deadlock exists and appropriate procedure must be initiated. Now it will find that there is a deadlock P3 to P1 to P3, P3 to P1 and P2 to P1. So in this particular case, if I take the example P1 to P3, P3 to P2, P2 to P1 is a cycle and that is not involving the PX. Hence, it is concluded that the system is in a deadlock state. Now, if this cycle is not present, then there is a second part of that. If the cycle involving node PEX is found in the new CFG at the site Sj, Sj send a deadlock detection message to the appropriate site Sk. And whole process is repeated by the site Sk. And in this manner, a finite number of deadlock detection messages transfers from one site to another site till the deadlock is detected. So if the newly constructed WFG at the site Sj contains a cycle without involving PEX, it's all right. It will declare that there is a deadlock detection. The deadlock is detected. There is a deadlock. But if this kind of cycle is not available and the cycle is available which involves the PEX, then in that particular case, this particular site will send a message to another site, that is Sk. And in this way, it will go on, it will proceed further. So this is how the deadlock is being detected with the help of WFG based distributed algorithm, and proper steps have to be taken, because once we are following these two rules, the first part of the algorithm, whether it is involving it or not, if it is involving, then it will send a message along with the WFG which contains a cycle, and the site S2 will be updating its WFG by including those edges which are not involving PX. And after doing that, if it finds that without involving PX at that particular site S2, if there is a cycle, it means there is a definitely there will be a deadlock. And if it is not so, and there is a cycle existing in that site S2 which involves PX, so what it will do, it will send same kind of the message which a site S1 has sent to S2. S2 will send to S3, and similarly the S3 will perform all those functions. S2 will be sending a detection message to the S3, and S3 will do all this processing. So in this way, the deadlock is being detected. Now, but this algorithm is having a certain problem. The problem associated with this algorithm is very simple. That if it may be possible that two sites may initiate the deadlock detection algorithm independently for a deadlock that involves the same process. For instance, if you take an example here, in this example, S1 is a site and S2 is a site, and S1 has almost simultaneously, both the sites have simultaneously detected that there is a cycle, that is PEX, P3, P2, P1 and PX, and it is also detecting the cycle, that is PEX, P1, P3 and PX. So both the WFG, which is maintained locally at the different sites, are able to detect that there is a cycle, and both may be detecting the cycle simultaneously. So if there is a cycle, both S1 and S2 will be sending a deadlock detection message to the other sites. And if it is so, what will happen? The result will be that the both sites will update their local WFG and search for the cycles. And after detecting a deadlock, both may initiate a recovery procedure, and the result may be very absurd. The result may be maybe the things by which it is going to kill some of the one or more processes uh, that is actually involved uh, in the cycle, in the deadlock, and it is required to resolve the deadlock. So this problem is the second problem is it is going to the extra overhead of the unnecessary message transfer and the duplication of the deadlock detection job is performed at both the sites. So this should not be done. So a modification, a solution of this problem has been evolved, and the problem of this solution has been given. And one of the way by which the problem can be solved by assigning a unique identifier to each process. Suppose P1 is a process, Pi is a process. So we will associate an identifier with the Pi. So if now once we allot identifier for each processes P1, P2, P3, P4, P5, whatever it may be, then and once it is identified, when the identifier has been allotted, now when a cycle is existing, such as Px, P1, Pj, P at a particular site, if it is found, the cycle is found at the local site, it will send the message only if ID of PK, the last one, if ID of PK is less than the ID of PI. Otherwise, the site does not make any action, does not take any action, and will wait for other site to initiate. So if there is a cycle at a particular site, the identifier has been allotted, it will check whether this last but one identifier last but one process identifier is less than the first process identifier or not. If it is so, then it will send the message. Otherwise, it will not send the message, and it will wait for the other site to take the action. So the modified algorithm says that by assuming that ID P1 is less than ID P2, ID P2 is less than ID P3, if this is the sequence in which the identifier has been allotted. Now suppose both the sites P1 and P2 has simultaneously detected the cycle, that is PX, P3, P2, P1 and PX, and PX, P1, P3 and PX. These are the two cycles it is being identified, but identifier has been allotted. Now, since ID of P1 is less than ID of P3, this ID of P1 is less than ID of P3. So it means site S1 will initiate, but site S2 will not initiate. Or why? Because S2 has the cycle P1, PX, P1, P3 and PX, and the identifier of P3 is greater than identifier of P1. So what it will do, S2 will not initiate. So it will be the process by which S1 will be initiate the deadlock detection message. It will send the message to the site S2, and once this message is being received, it will modify its WFG and detect whether they try to detect whether there is a deadlock or not. So this is WFG based, and it is also known as path pushing algorithm. Now the second one is the next algorithm is the probe based distributed algorithm. It is also known as edge chasing algorithm. This probe based distributed algorithm for the deadlock detection, it is basically known as CMH algorithm, that is Chandy, Mishra and Haas algorithm, and it is considered to be the best algorithm, and it is simple too. It allows a process to request multiple resources at the same time. This algorithm is conceptually work in the manner in which the algorithm has been explained, and it says that when a process requests and fails to get it, meaning thereby when a process that requests a resource or the resources fails to get the requested resource or the resources and time is going to be out, it generates a special probe message and sends it to the process or processes holding that request resources. जिस कोई भी प्रोसेस उस रिसोर्स को हेल्ड किया होगा, उसके कब्जे में होगा, उसको ये एक प्रोब मैसेज भेजेगा. And this probe message contains the following field. What are those fields? The first field will be the identifier of the process just blocked, and in this case it is the process P1. The identifier of the process sending the message. The second identifier will be the process who is sending that message. And the third identifier will be the process to whom the message is to be sent. So these three unique identifier will be sent in the form of a message, in the form of a probe message. Whenever it is being received, whenever this probe message is being received, it can be ignored or it can be forwarded by the received site. Now, on receiving the probe message, the recipient checks it to see whether it itself is in waiting state of any resource. If not, it means it is busy. It means the recipient is using the resources requested by the process that sends the probe message to it. So in this particular case, the recipient simply ignores the probe message. If message is being sent by a process P1 to the process P2, and process P2 is using that resource, then P2 will ignore that. But if process P2 is still in waiting, and as it has requested some resources from other side, then it will forward it to another process because it is still waiting. The process who has received the probe message is also waiting for another resource which is held by another process, so it will forward it. But if it is busy with that resource, it will ignore that message. So whenever it will be going to forward the message to another process, before forwarding it, it is going to update its field. That process who has received the message, it is going to update its field. The first field is left unchanged. उसमें कोई change नहीं होगा. And it updates the second field by its own process ID. And the third field is updated by the identifier of the next recipient of this message. Now, the third step is every new recipient of the probe message repeat the procedure, whatever is being explained in this step number 2. And ultimately, if the probe message returns to the original sender, it means there is a cycle and system is deadlocked. So the first is the process sends a request. If it fails to get the request, if it fails to get the reply, it will send a probe message, and probe message contains these three identifiers. And whenever it is being received, it is being received by, and it will, if it is busy, it will ignore. If it is not busy, it will forward. And if this process will continue till the probe message returns to the original. Let us see this example, then it will be more clear about the this algorithm. Now in this site S1 and S2, there are two sites, and suppose that the process gets blocked when it is when it requests for the resource which is available at P3. So it is in the wait process, so it will send a probe message, and the probe message will say P1, which is the sending site, P1. Second is the identifier of the process who are sending it, that is P1, and to whom it is sending it, it is P3. So the, P1 generates this probe message, P1, P1, and P3, and it will send to the P3. When the P3 is going to receive this message, it discovers that it tries to find out that whether itself it is blocked, or it finds that it is blocked by the process P2, as well as it is blocked by the process P5. So there are two processes which is blocking the process P3. So P3 will forward a probe message, but containing the first identity element as it is, second replacing by its own identity, and to whom it is sending will be the third identifier. Now process P5 is busy. It is not in the wait state, so it will ignore this message. And P3 will also send a message to the P2. And whenever it will be sending the message to the P2, it will, first element will remain as it is, second element will become P3, and to whom it is sending, it will become P2. When it is being received by P2, so P2 is still in the waiting state because it is waiting for the process P4. So it will generate probe message and it will send it to P4 by updating this value as P1, P2, and P4. So this process is busy, so it will ignore this message. And P2 will also send, because P2 is still waiting for P1. So it will send a message to P1 by P1, which is the first identity, second is its own, and third to whom it is sending, that is P2, P1, P2, and P1. So it means the message has been started from this place, it has reached to P3 and reached to P2, and again it came to P1. So it means deadlock is detected as in the form of there is distributed deadlock P1, P3, and P2, because P1 and P2 are the processes of the site S1 and P3 is the process of the site S2. So there, and P1 is waiting for the process P3, P3 is waiting for the process P2, P2 is waiting for the process P1. So this shows that it is a deadlock. That is why this algorithm is said to be the best algorithm, because of the features, different attractive features of this algorithm. The first feature of the CMH algorithm is it is very easy to implement, since message is of fixed length and require only very few computations are required in the different steps. The overhead of the algorithm is fairly low because there is no overhead. And ग्राफ का भी बहुत ज़्यादा कंस्ट्रक्शन नहीं हो रहा है, इंफॉर्मेशन भी बहुत ज़्यादा कलेक्ट नहीं की जा रही है, फॉल्स डेडलॉक बिल्कुल नहीं डिटेक्ट किया जा सकेगा, and it does not require any particular structure among the processes. So these, because of these attractive features of the CMH, and as you have seen that in the previous algorithm, whatever has been discussed, it was having a lot of computational efforts has to be taken, a lot of graph has to be made, but in this case, it is very simple, and that is why it is preferred more than over the rest.